Hi everybody. So I'm Raul Abramo. I'll be talking to you about cosmology and large-scale structure. By the way, I see many people here that took my relativity course just a few, even a few weeks ago. So for those people, it's going to be, it may be a little bit boring for you guys, but for everybody else, I hope you can get something out of this. So this is me here. I'm from the University of São Paulo, the other university here in the city. It's a huge campus, a very nice university. It's one of the best in Latin America, in the world. And we have a huge physics department there, Physics Institute, with more than 100 researchers. Pretty much all fields of physics, from all kinds of experimental physics to all kinds of theoretical physics. So you're welcome to also take a look and visit and let me know if you want to stop by the university and let me know, and I'll talk to you there. Okay, so you're going to be my test subjects because it's the very first time that I teach in this way, and I'm going to do most of what I'll say is going to be written like in a blackboard, but every once in a while there are some figures and some plots and some elements that I'll show to you as in a slide. So it's mostly blackboard in there, but it's the first time that I do this. So, you know, thanks for being in some sense, cobayas. That's how we say in Portuguese. And if it doesn't work, then next class I revert to the blackboard, okay? So be completely frank at the end and say, oh, no, this was terrible. Just go to the blackboard. What the hell are you doing? All right? And of course, interrupt me at any point if you have questions. So, lecture number 1 here today is going to be about some of the elements here. So, it was very nice that Pedro already introduced some concepts that I'm going to use, like what is a space, what is a metric, what is it there for? It's for measuring distances. And I'll talk about a very specific type of metric because that's what we believe describes the universe on its largest scales. And it's called the Friedmann-Lemaitre-Robertson-Walker metric. This metric over here, which has a special place in cosmology because it has some symmetry properties that we believe are realized in our actual universe. I'll talk about a little bit about the dynamics, more of this in the next lecture when I talk about the Einstein's equations and what they mean for the evolution of the universe. In this lecture, though, I will be talking mostly about how to do very elementary things like measuring distances and how do we actually understand that the universe is expanding by making measurements, of course, right? So the very first thing that I want to talk to you about is spatial curvature. And we have already met some cases here, and thanks Pedro for this. And I'll give you 2 examples of surfaces that you are familiar with. One of them is the Euclidean plane. I'll be talking here just for visualization purposes in 2D surfaces, but of course you can always think about 3D surfaces as well, or volumes. And these are 2 types of surfaces, and one of them has a familiar shape. This is just the Euclidean plane here, right? So this is the Euclidean plane over here. And then you have also basically the surface of this sphere here. Let's say that it has a constant radius r0. And then we can, oh, I opened up the 2 wrong things here. Jesus Christ, I already screwed up something in my lecture notes. Sorry, I'll start over here. Sorry. Let's see if I get it right this time. No, I got it wrong. I finished this now, and I do this now. Let's see. Hey. Yes, thank you. What the hell is going on? I have 3 things now. I have one there, one here, another there. Oh, Jesus, already. Let's see here. Let's start all over completely, okay? I'll just... Oh, no, now I know why. I have this, and I have this. All right, so I think I know what to do now. Jesus Christ, no. You know what? I think I'm going to erase all of those, start over. Okay, and now let's see. No, it's the other way around. Thank you for being patient here with me, guys. Okay, so let's see. This, and now this. Jesus, not again. It's the other way around, sorry. This, and now this. Ah, okay, good. Wonderful, there you go. All right, so I spent only 5 minutes doing that, huh? Okay, so coming back to our two surfaces here, what I wanted to show you is that these two, they look different and they are different. So in the case of the first one here, we know that we can write the distance as just in the simplest way that we know in terms of these Cartesian coordinates. But we could also write this in terms of, let's say, polar coordinates, right? So with some radius rho, and then some angle phi, right? In the case of the second one, which is this closed surface over here, right? Over here, we can, the actual metric for this is slightly different, as you all are aware. And we saw Pedro already giving basically some example of this here. And we can write it in this form here, right? This is, therefore, how you measure any kind of a distance along these surfaces. This distance, that distance, or the distance along here, or along these 2 points there, things like that, right? All right, so they have similar properties, these two surfaces, okay? They have the following properties. Similar properties. First, there is no center. There is no special place here, right? Any place in any of these two surfaces is the same. You can be here, you can be there, there, there. Any of these places is equally good as a reference point. For instance, you can put the origin of your reference frame here, or there, it doesn't matter. And you can put your axis here, either here, but you can also put it in there, you can put it in there, it doesn't matter. You have no special place where you can live in any of these surfaces here. But there's another property here, that if you are somewhere, then it's equivalent to walk in any direction, so all the directions are also equivalent. Here. So what this means is that, let's see if I can change now my color here. No. What this means is that we have properties called homogeneity, the first one, and we also have something called isotropy. Right? So you can go, if you see your universe, if you're a being that lives in that surface, if you look around, you'll see exactly the same thing in all directions. And what these properties mean is that this guy here means that you have invariance under translations and this means invariance under rotations also. Right? Okay, but what if I told you now that there is a third surface that has these same properties, but you cannot really see it immediately? It's different. It's similar, but it's different than the other two that you're seeing here. And the best way to construct this third surface, which has all these properties, so it is homogeneous, it's isotropic, but it's neither one of those two. By the way, realize that in these two surfaces here, if you draw, for instance, something like, let's say that in this surface here, I draw something like a triangle, right? If you sum the angles of these triangles, any triangle, you will have 180 degrees, whereas if you do this on this surface here, you get a little bit more than 180 degrees. So you could imagine if there isn't a surface where the sum of the angles of a triangle is actually less than 180 degrees. And it turns out that there is such a thing, okay? So the best way to see that there is this other homogeneous and isotropic surface oops, I can also erase isotropic surface is the following. In the metric for the sphere, we just take theta and we write it as something like R0 times theta, such that d theta is equal to 1 over R0 times this new variable here. I'll call this by the letter chi, that's the Greek chi. So this is now d chi. In such a way that now your metric for the sphere, it becomes really, it was really before zero, this metric here, right? And then it becomes now in this new, with this new coordinate here, which I called chi, it becomes this. Notice that the this dl square is really a distance square, so it has the dimensions of distance square as it should, right? Now, in order to see this third surface that has appeared, that obeys the same properties as the other ones of homogeneity and isotropy, what I'll do is that I'll take the following trick. I'll take R0 to be imaginary, so I'll just multiply by I. This means that R0 square becomes minus R0 square. And it also is true that if you do, if you look at this, this sign here, right, it goes into the sine square of minus I chi over R0. And then if you just open this using Euler's formula, you find that this is minus hyperbolic sine square of chi over R0. Okay? So what we have now is the following metric, and you can then reconstruct what the surface has to look like in terms of this metric and this and the metric is the following here. I'll just copy from what I just wrote to you there. It's going to be your chi is here exactly the same, but then now instead of having a sine here, you have a hyperbolic sine of chi over R0. So this is, if you look at this metric here and you reconstruct what the surface has to look like, it looks a bit like what you're seeing here. It's a saddle. You can see this is kind of a, what you can, if you just set a point and then you look at the different directions, this is what kind of what it looks like. However, this surface is very much real, and moreover, just as in the sphere, you can just move your poles or your centers or any point around by doing rotations. Here you can also do a rotation. This is a hyperbolic surface, and it's basically a rotation in hyperbolic space. And you can also show that it's also, oops, also homogeneous and isotropic. So it's also a surface where there is no preferred place, there's no preferred direction. By the way, all that I'm saying here is for the most part in those lecture notes that I put online. I'm not following exactly the way that I put them in lecture 1, 2, 3, and 4, but it's mostly there. So this derivation, for instance, is there also, but I strongly advise you that you can look at this. So the first people to find this surface here, and they did that independently, was none other than Gauss himself. Then also a Russian mathematician called Lobachevsky. I don't remember exactly how I write his name. I think it's this way, Chevsky. And also a Hungarian mathematician called Bolyai. I think it's this way that you write this. Right? And of course, you can also generalize this to 3 dimensions. It's just, in 3 dimensions, all you need to do is instead of having 1 angle variable, you have 2 angle variables, right? So, oh, it's hard to write in here. Having to find, okay, so this is now the regular theta that we know from spherical coordinates and this. Now, it would be nice if we could just put all of these surfaces into a single standing, because they look like, you know, if you imagine that you have a ball here that becomes larger and larger, right? It's clear that in some sense, something like what Pedro described today, that, you know, if you can put a patch on the surface here, which is basically an Euclidean patch, the surface right there looks pretty much like an Euclidean surface, right? So in some sense, there's a limit under which all of these surfaces, they kind of look like the same thing, and they actually can be described in mathematically in very similar ways. And it turns out that this is completely true, and that what you can do is that you can write all of these 3 surfaces in the following way here. So you can write all of them in 3D in the following way. You can, first of all, the radial distance is here, as it should, it's always there. But then there's a piece here, which is where this constant has dimensions of distance, what I called radius in the case of the ball, of the sphere. And then I'll call this, instead of calling this R0 square, I'll give it a different name. I'll give it a name of 1 over this k here. And I'll use here a sine square of square root of this k times our radial distance, and that is multiplying this there. Okay? So this is our first important formula of the day here. this is the most general metric for a homogeneous and isotropic 3D surface. And you can see that if you have this K here being, if you have this K here being, oops, let me write in black. Stop. No. Okay. I'll get it right eventually, huh? Yes. Yeah, sorry. Thank you. I said the theta and I wrote something else, right? Oh, how do I get this? Okay, now, thank you. Theta, thank you. Whoever said this that I didn't see. Thank you. So, for instance, if your K is 1 over R0 square, you have your 2D ball. If your K goes to 0, then you have Euclidean plane. And if your K goes to minus 1 over R0 square, then you have the, let's say, saddle, the Gauss-Lobachevsky-Bolyai surface there. But the important thing here is that, in principle, you know, we want to have not only in our, ideally, we would think that the universe has no preferred place and has no preferred direction, right? However, that doesn't tell you, because ideally you would say, well, if I specify these symmetries, that should be enough in some sense to specify what kind of a space I live in, but it's not enough. You have these 3 qualitatively different spaces that you could live in, and it's a matter of then looking at the universe and having it decide whether you have one sort or the other, or the other, or the other. Okay? So these are the 3 surfaces that we can work with, and in principle, this is what we can look for in the universe, assuming that you have these symmetries of homogeneity and isotropy. Now, of course, it's not a given fact that we have those symmetries. Of course, look around here. The universe is not isotropic in the scales of us here, of human beings. They are not even, the universe is not even homogeneous and isotropic on the scale of the galaxy, because we have our galaxy here, we have another galaxy over there, another over here. It's only on very, very large scale that the universe becomes homogeneous and isotropic. And this is a matter of, really, observations. Observations have so far proved that the universe seems to be homogeneous and isotropic as far as we can see. Okay? So that kind of squares with our principle that there should be no preferred place or direction in the universe, right? So we have these 3 surfaces here. So this is the surface that we call the closed surface. Whoops, let me go back here. So this is with positive curvature. So this is closed. We call this closed. This is with 0 curvature. That means that your radius, you can imagine that the radius of your ball goes to infinity, and it's equivalent to Euclidean space. And this is flat Euclidean, or this curvature can be negative, and this is called the open spatial section. Okay? Notice, however, that for very small radial distances, they all look very similar. That is to say that if you put a flat sheet on a small black sheet of paper on the, let's say, on the north pole of the ball, or on the lowest point of the saddle seam from where it's convex, then you can put a page there and it works. It's basically a flat surface in there. And I'll come back to this because it makes some simplifications here when we're looking around the universe here. Okay, so let's talk now about, knowing now that this is what our space can look like, And given that I already told you that we observe the universe and it seems to vindicate this view, that there is no special place or direction in the universe, what can we say now about the universe that we live in? And then at this point, we will need some theory that gives you a metric and behavior for not only space, but for space-time. So what we need now is a theory for space-time. And this theory here, as far as we know, is general relativity. There's nothing, no observation has ever detected any deviation from general relativity. So this is the theory that we have to work with. Okay, so so when Einstein actually found his equations for the for this metric, and people started playing with that, people soon realized that these surfaces that we just saw, they could very well describe the universe, the spatial part of the universe. However, it was still possible. Spatial part could be well described by the metric we saw earlier. But there was another possibility here, that when we are generalizing the Minkowski metric, so I'm assuming that everybody here is familiar with spatial relativity here, right? So the Minkowski metric is this one here, right? Now, this dl square here is really flat, of course, in Minkowski metric. However, in general relativity, there was space for allowing the universe to still be homogeneous and isotropic. However, you could have the universe changing from time to time. So it's like you're looking at different times, and the spatial part of the universe is still homogeneous and isotropic, but it changes with time. Now, the way that it changes in time is described by a single function. So the time part here doesn't change, but the spatial part here, possibly with some curvature, it could get some time dependence here. And this was realized first by Alexander Friedman. Nobody paid a lot of attention to his solution. Then Georges Lemaitre, who was a Belgian priest and physicist and astronomer, derived the same equations, got in touch with Einstein. He provided a more elaborate description, and also critically, he was also in touch with people that were doing observations that proved that this metric made sense in terms of what people were observing at the time. We're talking here about 1920s, 1930s, right? So between 1920 and 1930. Okay, so the idea here is that, let's say that we have some, let's represent the spatial section of the universe here by some surface here, which I'll try to draw as best I can here. Okay, perfect. Now, suppose that you are some sort of a being here that lives in that. This surface here is representing really 3D space, all right? It should be clear. It's just that I cannot really dry 3D volumes so well here. Maybe in a couple of weeks after I'm much better with this damn pen here, I can draw these. But right now, let's keep to this, this figure here. So let's suppose that you are some sort of a being that lives in here. Suppose that you are a galaxy here. And suppose that you are over in this place. Suppose that somebody else is over in that place. Somebody else is over in this place here, right? Now, you want to describe how the universe changes with time. So I already told you that there's no way that the surface itself can be deformed because it has to retain this homogeneity and isotropy, right? By the way, this is called the cosmological principle, the idea that there is no center and no preferred direction. So what we do is that we establish here, in some sense, kind of a, let's put our coordinates in here, and let's just draw them here in this way here by making a grid, just like you would do for, let's say, X and Y here. Let me just try to draw this well. Okay, right? So now let's go back here, and let's say that we have this surface here on some initial time, which is called, let's call this T1 here, okay? Now, what this function of time that appeared in that metric that I gave you, so let me just write this metric here before again, right? Just so that you remember. This, by the way, is called the scale factor. Okay? And by convention, today, at time called T0, A is equal to 1, okay? So, let's say that at some time, T1, it has this shape that we're looking at here, right? So, I'll do a nice trick here that I learned this morning. Oops. All right, this way here. Let's see here. I'll select this guy here. Oh, no. Again. Okay. And now I'll copy this in here. Let's say that at a different time here, the same surface appears, but now let's say that your scale factor grew, right? So it is possible that, for instance, if your scale factor went up, that this is what you're going to see, right? So all the distances are increased in the same way, because the scale factor multiplies all the spatial distances there, right? So this is what you would see if the scale factor was growing. Now, of course, so this is sometime T2 here, right? So of course, we don't know how it's changing, if it's even growing or if it's getting smaller, what is driving its evolution. I'll tell you next class how we can actually tell, how we can calculate the time dependence of the scale factor in terms of physical quantities, like what's out there in the universe, okay? That's what Einstein's equation tells us, how to compute this A of t, and this is the Einstein field equations. I will not derive the Einstein field equations, I'll just write what they are for this space-time. Yes? Yes, that's a very good question. I'll tackle this question by the end of this lecture, if I'm not, yeah, if I hope I can get there. Let's see. I'm going a bit slow because I'm learning how to use this, but that's the idea, okay? That's a very good question. What happens when the scale factor, which is, by the way, you can even write this same metric here in terms of, in a conformal way, so that the scale factor multiplies everything, even a new time variable here. What happens then, right? And something very interesting happens. I'll come to this very soon, okay? Now, so what we have shown here is that we can have the coordinate distances, which I'll call this, and these are the distances that you can measure by looking at these grids here, right? all right? These coordinates there, the spatial coordinates. But if you want to actually have the physical distance, you want to multiply this by whatever the scale factor is at that moment. And that is the physical distance here in this way, right? And of course, this makes all the difference because what we measure are physical distances. By the way, today, at this moment of time, by convention, we set both of them to be the same, but if you look back in time, they are not the same, and then you have to take into account this. If you're making any measurements in the universe, if you're looking away at a galaxy which is far away and therefore far in the past, you have to take this into account, okay? So this is, therefore, the physical distance. And this is what we call the co-moving distance, or the coordinate distance, if you want, okay? It's interesting, and I'll not show here, but you can look at my lecture notes, that if you're familiar with the geodesic equation, okay? If you put a particle at rest, if you put even two particles at rest, any number of particles at rest there, in some initial positions in your grid, and if you let time pass, they stay exactly at the same place. They don't move. So the time dependence that I'm talking about doesn't move the particles. It moves everything, but it doesn't displace particles with respect to that grid that I just drew to you here, okay? They stay exactly where they are. This is what by the way, I drew in here, in these two plots here. And here, they are in the same place here, okay? Now, now if this is true then, it follows that particles which are in that grid, in that space, but are far away, okay? It means that they are getting, let's say that the scale factor is growing, it means that they are getting pulled away from each other. You can even imagine that you are one of them here, that you live in our galaxy here, the Milky Way, and you are observing another galaxy over there. And the fact that you have some distance to that galaxy means that you will see that galaxy, if the universe is expanding, you'll see it running away. How exactly? Well, let's see that the distance here, the physical distance, is changing with time. And this is, of course, the time dependence is all in this scale factor because the coordinates of any test particles in the space are fixed. The geodesic equation tells you that they are not going anywhere. So this is just this derivative here times this constant here, RC. So I can write this as the following way. I can write this as, oops. I'll just use a dot here. Okay? For time derivative. And this is therefore, you have found something which is a relationship between the velocity and the distance. So basically this is the velocity, the physical velocity with which this galaxy is moving away from us. And this is given by a direct relationship with regards to the distance here. Okay? Now, this function that we found here is so important that we give it a special name, and it's called the Hubble parameter, or the expansion rate. And it will play a very important role. Expansion, well, it could be negative if the universe was contracting. However, we know it's expanding, so we just call this expansion rate. We should really call it the rate of change, or... Okay, so that's a very special function that will appear everywhere. And if we know this function, of course, we can integrate it back and find what is the scale factor with time, for instance. So knowing the scale factor as a function of time, or knowing the expansion rate as a function of time, is basically the same information, right? Okay? Now, so what I told you then is that there is a kind of a, if you look at these, at our surface here, right? We'll have particles in many different places, and they are all moving with respect to each other. So you can, you can take the point of view of this guy here, and for this guy, this galaxy will be moving away. You can take the point of view of this guy here, and from his point of view, this galaxy will be moving away, and so on and so forth, right? So how do we actually detect? So this is the most direct way in which we can detect this effect in our actual universe. So we should be able to detect this. But how can we detect this drift? In the universe, right? So what we need is to measure at the same time both the velocity, v, and distances, d. We have to be able to measure both of them, otherwise we cannot really measure this expansion rate, right? And this is a very simple thing, yet a very nasty, complicated thing that is at the heart of many of the issues in cosmology. And the issue is the problem that we cannot really measure distances. Velocities we can measure easily through the Doppler effect, but distances are a whole different matter. And it's extremely hard to measure distances in the universe. And we do all kinds of tricks to do that. Not only that, but there are different types of distances in the universe. So if you want to do a plot like what I'm showing here, right, what I need is to measure both this and that. Now, it's simple enough to measure velocities. Because of the Doppler effect. And basically the idea is that we are here, and if we see some source of light here, say a lamp here, which is moving away from us, which is at some distance, say from us, and is moving away with some velocity v, right? It emits light with some frequency here, which I'll call emission frequency, but when it reaches us, this frequency goes down, and I'm drawing here the wavelength going up, right? So this observed frequency is lower by the factor given by the Doppler effect. So basically, this is for the frequency is this factor here, and for the wavelength is the inverse of that, because of course the speed of light is the same. Jesus, I'm not being able to write any straight lines in here. Okay, 1 plus v over c, 1 minus v over c, lambda. And we call this actually, this factor appears so much that we call this the redshift. So this here, I don't have space to write this, but this is called the redshift. So whenever something is moving away from us, the redshift is positive. So the wavelength gets larger, the frequency is lower, right? If something is moving towards us, and in fact, some of the nearby galaxies are actually moving towards us. So Andromeda galaxy, for instance, it is in our vicinity, and we share a common gravitational potential, and it's actually, we are in a collision route, but it's going to take hundreds and hundreds of millions of years for this to happen. But this galaxy has a blue shift. It's actually moving towards us, just a little bit, with some, I don't remember, something like 200 kilometers per second, something like this, a small velocity. For cosmological scales, it's a small velocity. Okay, so, but how do you measure distances? This is now really the key here, right? So, traditionally, you can use the idea of parallax. This is, the idea is that we have the sun here, and we move around the sun, right? And we are sometimes over in this place, sometimes we are over in this place. And if there is a star here, which is sufficiently nearby, when we look at from in January and then again in beginning of August, we see this, let me see if I can get this now, in two different directions. Here, and oops, no. I'll get the gist of it eventually. We see this in two different places, separated by some angle, let's say theta here, right? If we know what this distance is, let's call this here, I'll call this d, okay? Then we know that the distance to that star, in the limit where this angle is small, of course, is that this distance is basically d over theta. Now, this is a true and tested method. You can do this out on the street if you want. We can do this for nearby stars. Then you run out of stars. This game people started doing as soon as they had telescopes, because they looked at the stars around different times of the year, and they saw that some of the nearby stars were doing kind of a circle in the sky. That's parallax. But if you really try to go farther away, then you need better telescopes, then you need a space telescope. And then right now, today, the best space telescope for measuring these kinds of parallaxes is called the Gaia telescope. It's already finished its operation, so it's not working anymore. But Gaia was able to map basically all of, basically the Milky Way, from our position to the middle of the Milky Way, pretty much. So it's mapped basically half the Milky Way. It cannot go further than that. Even the best satellite, the best space telescope. So, you know, if you're hoping to measure distance to galaxies, forget it. This is not the way to do it. We can measure distance to millions and millions of galaxies, and Gaia has like, I think, almost like close to 1 billion galaxies with parallaxes well measured, but for galaxies, so stars with parallaxes well measured, but for galaxies, forget it. So how do you do it? Well, so how do you actually measure cosmological distance, not of astrophysical distances? So it turns out that in 1920, an astronomer called Henrietta, leave it, I'm not sure if she has two T's in Henrietta, maybe just one T. She noticed something very interesting happening with some very bright stars called Cepheid stars. And she found the following thing. She noticed that if she plotted the luminosity of those stars, the absolute luminosity, so that means how many lumens it emits, for instance, right? It's not lumens, of course. Astronomers use other units, but and then you plot this against the period with which they oscillate. So their luminosity is basically some L0 cosine of 2 pi t over t. So she noticed that these stars, they showed some really interesting properties, that the bigger the period, so how the slower they were to oscillate, to pulsate really, the larger their luminosities were. Notice that these were stars for which she knew the distances from the parallax. So she could calculate on the basis of the apparent observed luminosities here on Earth, their absolute luminosities. Of course, right? You have to invert for the square root of the distance to do this, right? But she figured that this was happening here. So basically, she found that there is a law here that basically you can trace here. And this is basically what allows us to do the following now. Let's suppose that you see Cepheids in another galaxy, which, by the way, you can, because Cepheids are super bright. They are like 100 to 1,000, sometimes 10,000 times brighter than the sun. So suppose that you have a star whose distance you don't know. So the luminosity you really don't know, right? But suppose that you have this, you find one for which you know what is the period is. You measure this for one such star in another galaxy. You can come back here and you can invert and find what is that L star for that star. And now, of course, you can then do the magic trick, which is that, well, now that I have this luminosity, I can, so you go from the period to the absolute luminosity, and then you use the fact that the flux that you measure for that star is really the luminosity divided by 4 pi times the distance square, and then you find this. So this is the way in which we can measure distances to some of the nearby galaxies for which we could never get parallaxes. By doing this trick here, of course, it is a phenomenological thing, and it's not exact. However, astronomers got good enough in the business of understanding the structures of stars that they can actually have models of these stars which are near perfect. So there's a theory for these pulsations of these stars. So this is not just phenomenology, it's really a well-grounded, there's a well-grounded theory for how these Cepheids pulsate. Yes? What's inside the cosine? I don't understand. My writing is pretty bad. 2 pi times t. 2 pi times t. T over t. It oscillates in time with some period. So basically, if you look at the flux from these Cepheids as a function of time, it oscillates. It goes like this. And this is the period here. Okay? It's not exactly a cosine, but it's near enough. Okay? All right, so that's how you get some distances. And this is exactly what Hubble did. Edwin Hubble, in 1929, he used exactly this technique to find the distances to many nearby galaxies that people were calling at the time nebulae, because they were not sure if they were, star nebulae in our galaxies or nebulae in terms of whole other galaxies. And he determined for once and for all that these were really other galaxies, because this distance here was much larger than the distance to the Milky Way. By the way, 1 parsec, which is PC, is 3.26 light years. And this distance here is, say, 2 million parsecs and so on. So the Milky Way is only about 100,000 light years across. So this is, of course, outside of the Milky Way. Okay, so immediately it was clear, and Hubble realized this. By the way, Hubble was already in contact at the time with Lemaitre. And so when Lemaitre saw this, Hubble noticed this, Lemaitre noticed this, and it was immediately clear that they found that the universe is expanding. Okay, so that's the key observation there, in this way. Yes?
More as a curiosity, where do
Parsec. Actually, I don't know where the unit parsec. Well, the parsec comes from. It's related to 1 arcsecond. So it's a parallax of 1 arcsecond with 1 astronomical unit. I think that's where it comes from. But parsec, the word, I'm not sure. I don't know. It's a cool word because Star Trek used it, right? Because I don't know. I don't know how I don't know where it comes from. That's a good question. If anybody knows, please let me know. If anybody Googles it, you know, like I'll give you 10 seconds to Google this. Sorry? Yeah, I think they use it, and they started using this for time, which is of course wrong. But you know, that's again, space and time is the same. So, what do you care? But I don't know what parsec comes from. No. Yeah, P arcsecond, so it has to be that, right? It has to be arcsecond. So yeah, no, it has to be parsec. Yeah. It's not parsec, it's parsec. I don't know, something like this. Yeah, asec, arcsecond, yeah, that must be it. Now, we have to be a bit careful here in cosmology, and I'll come back to this later, because there are many different definitions of distance. Remember that with time, your spatial surface changes, right? So what you really mean by distance and how you measure it is something that is subtle here, right? So one of the ways, so let's just remember here what is our metric here, right? Our metric is this here. And I'll write this explicitly here now in terms of the radial distance and also in terms of the angular part here, because both of them will come into what I'm saying now. So one of the ways in which you can measure distance is the following. It's similar to parallax, but not exactly the same. Suppose that you actually know the dimension of some system here of, say, a galaxy. Suppose that you know its diameter, which I'm calling here b, right? Then by measuring the angle that this galaxy occupies in your telescope, in your image, in the sky, you can actually derive what is the distance in this case, right? So we can say here that this b has to be this whatever is in here, right? So this really is the, sorry, let me just underline here. This part here is the part that measures distances in that way, right? You fix the radial distance and you vary the angle somewhere. So this is how you measure a distance across the radial direction, across the line of sight. It comes from here. So this b here has to be then that distance, a of t, 1 over root of kappa, sine of square root of kappa chi, times this theta that you measure there, right? Now, this, so of course, and then you can invert this. This is what we call here the angular diameter distance, dA. So this is called the angular diameter distance. It's very physical. It's easy to interpret. You know, it's basically the same principle as parallax, right? The other way in which you can measure distances is kind of reciprocate of that. So imagine that you have some luminous source here with some luminosity L that you're observing at a radial distance here, which I also call chi. Then what we call the luminosity distance is actually, it has the same factor here. Oops. However, instead of having the scale factor there, it has 1 over a here. And you can see why in my lecture notes, but basically the idea here is that when light comes from this star all the way to us. It suffers, its energy goes down, so the flux goes down because of this, but also the rate at which these photons were emitted at this star, that rate also goes down because of the Doppler effect, if you want. So there are two factors. So you take the angular diameter distance, you divide by a square, and you have this here, okay? For a longer derivation, for a more detailed derivation, you can look at the lecture notes, okay? But that's another way in which you can measure. So the idea here is that you can infer the distance here from the flux. So if you do this here, the square root of L divided by 4 pi times the flux that you observe, then that's called the luminosity distance, and it is related to the coordinates of your spatial section in this way. It has that difference factor of the scale factor. Remember, the universe is changing. So suppose that you know that the universe is expanding. That means in the past it's smaller, right? So if you look out for something which has a certain fixed physical size in the past, it occupies proportionately a larger place than it occupies now. For the luminosity, it's kind of the opposite, because the photons, they had some energy and some rate of emission, and that goes down as the universe expands. So that's the difference, and that's the reason for the different definitions. Of course, the actual coordinates of some object are, of course, the same. In both cases, if we could, for instance, measure both luminosity, and we also had some angular diameter distance, we would come to the same coordinates, of course, right? So this is just a way of defining how we measure distances and how we can then find the coordinates, right? Okay, so I was going to say something about something more interesting about the light cones in these space-times, but I was a bit slow, and I think tomorrow I'll come back to this, because my time is now up, I think, Pedro? Yes, so I'll continue this tomorrow, and hopefully a bit faster than I did today. Anyway, so that's it. Let's stop for now, and I'll take some questions there. So it wasn't a total disaster, as I thought.
Questions?
Hi.
Hi.
If the wavelength is getting bigger because the universe is expanding, and the photon energy depends of the wavelength, it means that the universe is losing energy, or where is going that energy?
That's a good question. So there's no conservation of energy as such in general relativity, okay? There's conservation of the energy momentum tensor in that sense, right? So there's no reason why the energy should be conserved, and in general, it's not. You have a conservation, you have a local conservation of energy and momentum, in the sense that if you move energy from here to there, you have both a momentum, a current, and the energy increases here and lowers in there. But for the universe as a whole, there is no such thing as a conserved energy, except in very, very particular cases, okay? So there's no reason why we should have conservation in that sense. So nothing is, it's not like the photon is losing energy and somebody else is getting it. No, there's no such thing, okay?
Is you losing it? Is you losing energy? Or
Well, it's not so, there's nowhere to lose energy to, right? It's not going anywhere. It's just that there is something called continuity equation for energy and for momentum, in this case pressure, which tells you how the energy is changing, how the energy density is changing. But again, there is no energy conservation. So there's only local conservation of energy momentum tensor, but there is no integral of that which has a conserved meaning. Okay?
yeah, thanks.
there exist any sense of asking where does the universe gets the energy to expand?
Well, let's put it like this. If you write the Einstein's equations, which I will in the next lecture, you realize that the expansion, there's a law called Friedmann's equation here, which I'll write here. I'll just write the first equation here, okay? That it says that basically, so this is basically writing the Einstein field equation here, okay? Field equations here. And you get the 0, 0 component here for the Friedmann-Robertson-Walker metric. And you find that that equation, the left-hand side, is basically the expansion rate squared, and the right-hand side is just the density, the total density of matter, energy, everything, okay? So at any moment, this is sourced by that, okay? So it's the energy, whatever content of the energy is in there. Okay, there's a second equation, but we don't need to look at this right now. So in some sense, at any moment in time, one is linked to the other. So in some sense, this is sourcing that. But of course, as time goes on, this has to change. So this is changing with time. So this is, and this is also changing in time, right? And there's a way of relating these two here, right? So the energy momentum conservation. There's a better. Is basically for a homogeneous anisotropic universe, it tells you that the variation with time of the energy density is compensated by the expansion rate, the energy density, and the pressure. So in some sense, this is telling you how your energy is going to change with time. So it depends on itself. This factor here, by the way, 3H is just the rate of change of the physical volume, right? Because this is just the co-moving volume, which is constant times scale factor 3 to the cube. But there is a pressure factor here, and that you can think of as whatever is doing work on your volume, just like in thermodynamics. So things can change. So this is what's sourcing the expansion rate at any moment. Now, of course, what happens right at the Big Bang, it's anybody's guess, right? But at any moment in time, it's really, this is where, this is the counter, this is what's fueling the expansion, right? Of course, again, notice that this doesn't tell you if this is positive or negative. You could be contracting, and then the more you contract, the more this grows, the faster you contract, and so on. And the opposite is, if you're expanding, this density is becoming lower, of course, because you're expanding, you're diluting things, and the expansion rate is going down. So you can have these two situations there, right? So our universe chose to be expanding, not contracting, but it could be equally there.
Thank you.
Pass the microphone there. Back to
Thanks. Is there anything? There are three types of metric. There are homogeneous and isotropic. And is there anything preventing the universe from going from one to another one In other words, is anything preventing the constant k to change over time instead of using only a scaling factor?
That's a very good question. If, let's say, in principle, these are constants. This is like Newton's constant or Planck constant, some property of the universe in principle, right? But that's in the strictly when you describe the universe as a homogeneous and isotropic manifold. This is not necessarily true. Probably it's not true in some sense, right? So you need to go beyond one of these models. So we have some models called Lemaitre-Thomson-Bondi models, for instance, where there's no sense of curvature. You can have one place which looks more like it's open in some asymptotic limit is open, another place is closed, and you have these bubbles, and they coexist. So you can move around. These are extremely complicated models, of course, but you know, it's in principle it's possible, but you have to move beyond. You cannot just you cannot frame that question within the Friedmann-Lemaitre-Robertson-Walker framework. This is, in that sense, that is a constant. You can move beyond by making the universe more complex, okay? And then, sure, you can find models where there's no such thing as a curvature. You see that when you do that, curvature is not a property of that space anymore. It's just some curvature, just like, you know, the Riemann curvature or the Ricci curvature, something like this. It has a property, a local property of the space in each point. Which our universe, by the way, is probably like this anyway, because on small scales, it's certainly not homogeneous and isotropic, right? I mean, I'm here, you're there. It's not homogeneous and isotropic for sure. On small scales. On large scales, probably it is.
Okay, thanks.
Questions? Okay, so we can take a 5-minute break if people want some coffee and cake, and then we'll come back for the discussion.